Next up is Billy Kline.
Good morning, everyone. I'm Billy Kline. I'm a first-year master's student in the Engineering Systems Lab, and I'm also a Space Operations Officer in the Space Force. And this morning, I'll be talking to you about my own master's thesis research, which is predicting orbit perturbations using machine learning. And just a quick disclaimer that any views I present here are my own and not that of MIT or the Space Force. So just to frame the problem real quick, why would we want to know what changes are happening to the orbits of satellites? Well, the reason we need to predict this is because while we always have a general understanding of where objects are in orbit, we always have track of these objects, so to say, we don't always have custody of them. And what this means is that although we can predict, generally speaking, where a satellite might be, it's not always in our field when to actually heed these warnings because they don't want to be wasting propellant by needlessly maneuvering. So what we want to do with our research is improving the orbit propagation algorithms by accounting for these out-of-sight maneuvers. Now, the tool that we're planning to use for this is machine learning. And the reason for this is over the past few years, we've seen machine learning improve on conventional methods of orbit prediction in many ways. And a few of the ways that previous research has targeted using machine learning to improve orbit estimation are by improving the satellite force model and by correcting for measurement error. So one of the ways you can improve the satellite force model is to improve atmospheric density modeling so that you have a better idea of the drag forces that a satellite is experiencing. And a paper in 2021 looked at how you can use machine learning to target that. And similarly, there was a paper actually back in 2019 that looked into adjusting for measurement error. So anytime you are predicting an orbit and then reporting a satellite track based off of that, you can get errors whether due to the sensor measurements or due to the way that the trajectory is reported. So for example, if you're giving out a two-line element set, which is a very common way of reporting a satellite's orbit, that has all sorts of imprecisions introduced into it due to truncation error, for example. And so there was a paper that looked into adjusting the predictions using machine learning to predict these errors. But what's important to note is that most past work in using machine learning to improve orbit estimation has targeted these systematic tracking errors. So whether that's an error in the force model itself or a measurement error, that's kind of what the past work has looked at. And what we're looking at is how we can make these models even better, even if they're already doing their jobs perfectly. We want to know if they can predict what's going on when we don't have custody of a satellite. So that leads to our research questions, the first of which is how can machine learning improve conventional methods of predicting trajectory changes, and that's whether that's due to station keeping or due to space weather. The second one is how much foresight is needed to train our models effectively. And the reason this is important is because we want to know if we can update our prediction algorithms in real time to enhance space situational awareness as we develop a better idea of a satellite's behavior. So this project is taking place over the course of several stages, and right now we're very much in the early stages of the project. So we want to start with a very baseline model, and that's just using an autoregressive integrated moving average model to predict the pattern of life behavior of a satellite, and then see if we can extrapolate where the satellite is going based off of that. From there, we want to try more machine learning models, such as PyMC, or the models that you can get using scikit to improve our predictions. Once we do that, we want to add in predictors of space weather. So that might be things like sunspot activity. And we also want to test our models using other types of data, such as vector covariance messages. And we want to see if these models will work and be able to account for this additional data. And the ultimate goal, as I noted earlier, is evaluating real-time improvements to the orbit estimation algorithms. And like I said, we're in the early stages, so we're just trying to build a baseline model using an ARIMA model, as well as some other machine learning methods on just a small set of data for now. So just to show where we're at currently, this right here is a Starlink satellite, Starlink 5652, and it's orbiting at an altitude of about 560 kilometers, although you'll notice that the orbit's not perfectly circular. And what we did was we wanted to see if we could just train an ARIMA model based off of the first, in this case, 58 hours of data. We're using the ephemeris data that we get directly from SpaceX for this. And then from there, we're just using the ARIMA model to predict the altitude going into the future. And you'll notice that the ARIMA model is able to more or less predict where that satellite will be. It's able to capture the periodicity of the orbit, but you'll also notice that it predicts that the troughs of the altitude are increasing a lot more than they actually are. So these conventional methods work, but they don't work all that well. And what we want to try is using other models that might work better than what we have here. So just to summarize, the false positive rate for collision warnings in space is far too high. Just to kind of quantify this a bit, Starlink satellites back in the first half of 2023 had to maneuver 25,000 times collectively in order to avoid collisions. And they maneuver anytime the models show a probability of collision greater than 1 in 100,000. And this rate could grow to 1 million maneuvers every 6 months by 2028. So this is a number that we really want to shrink so that satellite operators are not needlessly maneuvering and wasting propellant. And the way we intend to do this is by improving collision warning systems. And as I noted, a way of doing this is through better predictions of out-of-sight changes in the trajectory of objects in orbit. And so machine learning has already shown promising results in addressing other issues with orbit estimation. And so we want to see if we can apply this to the custody problem. And I just want to thank a lot of the people around MIT who have given me a lot of help with this. And these are the papers that I referenced. And if you have any questions, feel free to find me after this presentation. Thank you.
Thank you, Billy.